Hi everyone. Uh, so far we have discussed Schmidt triggers with that operate on dual supply voltages. Now in this lecture, I'll just introduce to the problem of single supply voltages and what happens if I just take the conventional dual supply Schmidt trigger circuit and then just use a single supply for it. Will the circuit work? Or what happens to the characteristics of the circuit? So that's what I thought I'll discuss in this lecture very briefly. Okay. In the next lecture, we'll see how to tackle the problem, how to actually design Schmidt triggers for single supply systems, or what difference is the Schmidt trigger circuits are there in the Schmidt trigger circuits for single supply systems. So here I've assumed a non-inverting Schmidt trigger and a non-inverting Schmidt trigger here. I've shown two Schmidt trigger circuits. Both of them operate on a single supply voltage. We'll very quickly draw the transfer characteristics of both these Schmidt triggers. First, I'll start with an inverting Schmidt trigger. So always, as I said, when you analyze Schmidt triggers, assume that your input voltage is minus a huge negative value and then start slowly increasing it. If the input is a huge negative value here, okay, what would happen to the output? Output will be positive. So output will be at plus VDD. So I'll assume instead of VSAT, I'm assuming it is at plus VDD. So if your output is at plus VDD, this node voltage will be at plus beta times VDD. So the positive node voltage is at plus beta times VDD. Okay, that's your V plus is at plus beta times VDD and your V minus is at VI. Right now VI is a negative voltage. So naturally you can see here V plus is greater than V minus. So your output will be at VSAT. Okay, which is VDD in this case. So output is at VDD in this case. So now I'm slowly increasing my input signal. At some point, the input signal becomes equal to beta times VDD. Okay, beta times VDD is still smaller than VDD. So at some point when your input exceeds beta times VDD, at that point V minus becomes greater than V plus. So your output voltage will go to logic low. Okay, in this case it will go to 0 volts. So your output voltage started from plus VDD. Here it was VDD. It reached 0 volts at beta times VDD. And then it will stay put at 0 after that. Even if you keep increasing the input voltage is greater than beta times VDD. So your V minus is greater than beta times VDD. And what happens to your V plus? The moment your output changes to 0, okay, the feedback voltage will also be 0. So if your feedback voltage is 0, V plus will be at 0 volts. So you can clearly see that V minus is greater than V plus, so output will stay at 0 volts. It's logic low, output will stay at 0 volts. Now I slowly start decreasing my input. As I slowly start decreasing my input, remember V plus is staying put at 0 volts. Okay, so as I slowly start decreasing my input, when will your output start making a change, or when will the output start transitioning? Only when your input goes lower than 0 volts. So only when your input goes lower than 0 volts, then your output will transition. So let me use a different color here. So at this point, your output will transition from a logic 0 to a logic 1. Okay. So the characteristic would look something like this. It goes this way, this way, this way, and this way. So this is your hysteresis characteristic. Okay. So the low to high threshold voltage is at 0 volts. The high to low threshold voltage is at beta times VDD. Now what happens to this circuit, which is our non-inverting Schmidt trigger? We'll do a similar analysis and quickly plot its transfer characteristics. And immediately you will see what is the problem with single supply systems. So again, when you are analyzing, assume that your input voltage is 0. If your input voltage is a large negative voltage, and a large negative voltage goes to the non-inverting terminal, output will be at minus VSAT. In this case, it is 0 volts. Output will be at logic 0 level, which is at 0 volts. So I'm going to assume my input is a huge negative voltage and the output is at 0 volts right now. Okay, so if this output is at 0 volts, the feedback voltage due to the output will also be 0. Okay, so remember, if you guys recall the non-inverting Schmidt trigger circuit, as I keep increasing my input voltage, what is the point at which it will transition? It will transition at beta times Vsat. Okay, it will transition at beta times Vsat. Now, because Vsat, the negative voltage is, it's not minus Vsat anymore, it is 0 volts. As I keep increasing my input, when your input reaches 0, input crosses 0 volts. Okay, when your input crosses 0 volts, your output will start to go from 0 to logic high. So the V low to high threshold will be, see, remember in an actual circuit, if you guys recall the circuit, I'll just do this. If you have already followed the previous lectures, great. Otherwise, I'll just quickly explain this in a very small step. Just find the voltage at this point, which will be what? R2 by R1 plus R2 times Vi plus R1 by R1 plus R2 times Vi, V0. Okay, what is the moment of interest to us? Right, the moment of interest is whenever this node voltage goes greater than 0 or less than 0. That's when the transitions at the output will take place. Okay, so I can write this as Vi plus beta times V0 multiplied by some factor, which is R2 by R1 plus R2, whether it's greater than or less than 0. Since this is just a constant scaling factor, I'll just take this term, which is Vi plus beta times V0. If this is greater than or less than, or if this is greater than 0, output will go to plus Vsat. Okay, if it is less than 0, your output will go to if it is less than 0, your output will go to minus Vsat. Okay, that's the transition point. So now what happened? Initially your input voltage is a huge negative voltage, so I didn't care about whatever it was adding to. That result will be negative, the net result. Therefore, I assume the output voltage will be at minus Vsat. In this case, because it's a single supply system, it will be at 0 volts. So because your V0 is at 0, now you have a condition Vi, the total voltage at the non-inverting terminal is simply equal to Vi itself. Okay, so when will the output go from logic 0 to logic 1? Whenever Vi becomes greater than 0. See, whenever V plus becomes greater than V minus, but V minus is at 0 volts. So your output will go to logic high whenever V plus is greater than 0 volts. Okay, since V plus is equal to Vi, because V0 is 0, you have the condition at which your output goes from 0 to logic high will be when Vi is greater than 0. So this is the point, low to high transition point. Now after this, it will remain, the moment your output goes to plus VDD, okay, plus Vsat, in this case plus VDD. Now what happens to your feedback voltage? The feedback voltage will become, so now the total voltage at the non-inverting terminal, I can write it as Vi plus beta times VDD. Okay, since Vi is now greater than 0, beta VDD is also greater than 0, the total will be greater than 0. So you don't have to worry, output will stay at VDD forever if you keep increasing your input voltage. Okay, it will keep on increasing. Now what I'm interested in is what happens if I decrease my input signal. If I start decreasing my input signal. So if I start decreasing my input signal, what I'm interested in is the point at which your output makes a transition. So if I start decreasing my input signal, you can see from this expression, when your Vi becomes less than minus of beta times VDD, that is when your output will go from plus VDD to 0. So when I change my input, decrease my input, when my input voltage becomes lower than minus of beta times VDD, that's when the transition happens. Okay, so this is how the transfer characteristics of a non-inverting Schmidt trigger with a single supply system that operates on a single supply look like. So the low to high threshold voltage is 0 volts and the high to low threshold voltage happens to be at minus of beta times VDD. So if you observe one very important property here, what you can see here is that for both these cases, For both these cases, the low to high threshold voltage is stuck at 0 volts. When your output is going from logic low to logic high, because your V0 is 0 and you're feeding back a part of V0, so the low to high threshold voltage is stuck at 0. Okay, that's the problem with single supply systems. Okay, so let me just show this graph. And in case of, I'll just draw it myself here. So in case of inverting Schmidt trigger or non-inverting Schmidt trigger, the low to high transition happens this way and the high to low transition happens at this point. Okay, so this will be minus of beta times VDD. So if you observe, there is a problem here. The problem is that one of the threshold voltages, especially the low to high threshold voltage in both the cases, whether it's an inverting or a non-inverting Schmidt trigger, is always stuck at 0 volts. If I just directly use this circuit, if I just directly use these two circuits as it is and operate them on a single supply, naturally your low to high threshold voltage is stuck at 0 volts. Now, since we have discussed so much about Schmidt triggers and how to design Schmidt triggers with asymmetric threshold voltages and all that, you can by now guess what are the ways in which I can change these transfer characteristics. Okay, you can use, or you can either add offsets or you can do some other approaches as well. So all those techniques, I'll talk about all these techniques in the upcoming lectures. Okay, thank you.